Okay, we're going to do a very quick little mini lecture to introduce a function called the stream function that is connected to the idea of streamlines that we talked about in class, and I didn't have a chance to define the stream function that's going to be very useful for some of the things that we do as we go forward. So this is a little mini lecture, if you like, that will introduce the idea of a function that we typically call the Greek letter psi. So this would be psi in LaTeX, and it's the stream function, which is particularly useful for a 2D incompressible flow. So imagine some general flow, any flow in it, if you like, where it's described by some streamlines, and I've sketched a couple of streamlines here. And the stream function essentially tells you a value, or is a value that is constant along a streamline. So like this function, this value psi here, along this streamline, and then we have another value, which we can call psi plus d psi, along a neighboring streamline. So if I was to take a little piece of material along a streamline, then we remember that the velocity is everywhere tangent to the streamline. And we introduce the idea that along a streamline, dx over vx was equal to dy over vy. And to indicate that we're following along on a streamline, we will use a subscript s for streamline. So along a streamline, that is true. But what about in other places? What about in other places in space? So what about if I think about general values of x and y like that? Then I'll move from one streamline to another streamline. And we might be interested in trying to understand what's going on between those. And so as I've drawn generically here, imagine two arbitrary points, A and B, and it's very close together. And so very close, as I bring these together, then where those streamlines are come together, we have a flow which is tangent to the streamline, which we'll call the velocity v. Okay? However, I've tried to be clear that A and B are arbitrary, and so if I draw a line to them, there is a normal vector to A and B, which we can say has a normal vector n associated with it, and we're going to derive a relationship that's relating velocity and n and the values of the streamline. Now, the first thing that we might note is that the values of the streamline are indeed material values, and this quantity has units of meters squared per second. And so the definition of the streamline, so which we'll give as a definition, is that Vx is related to the stream function by d psi by dy, and Vy is related to the stream function by minus d psi dx. And again, you can see that this has units, because if this is meters per second divided by meters, then this will give us the values of the velocity. And so we want to understand why this definition is made this way and what it's useful for. I'll also point out that there is an extension to 3D, where in 3D we might be interested in a three-dimensional body of revolution. And so we might be interested, for example, in flow past a sphere, as we've talked about. And then the idea is that if this is an axisymmetric body of revolution around here, then everywhere the velocity is tangent to the streamline. And so there's no flow across here, and people will refer to this as a stream cube. So that's an extension in 3 dimensions to what we're going to draw in 2 dimensions. Now, a very important quantity that we're going to want to think about is we're going to want to think about what is the volume flow rate, or the differential volume flow rate, that's associated with a velocity v crossing a little piece of surface in 2 dimensions, which has a normal vector n. And so we might indicate the surface of this by dA. And we're interested in the volumetric flow rate past there. And so the first thing that we're interested in is we recognize that any component of the velocity that's parallel to the surface doesn't correspond to any flow coming through there. So it's only the normal component that would be going through the surface that's relevant. And so we might be interested in calculating this quantity. And this quantity here would be called Vn. And Vn is clearly given by the dot product of n and v. And so, in fact, the volumetric flow rate going through the surface, which we'll call dq, is nothing but v dotted into n dA. Or we might write that in terms of the normal component of the vector, vn dA. So the first thing we can see is that indeed this quantity has indeed units of area times velocity, and so this is in meters cubed per second. And this is a general quantity that people frequently will show as kind of a the amount of material that crosses through this area per unit time, which is this amount of material, is indeed given by this quantity right here. And so we'll see how to connect these two things together in a moment. Okay, the final thing that we might need to remember how to do is to calculate an expression for the normal vector. And so if I have a function that looks like this, where I've got an n like this, I might be interested in thinking about what are the components of that normal vector. And so let's draw that out in a little bit more detail. So if I have a surface like this, and I have a normal vector like this, then I might represent it in terms of the steps dx and dy that I've made between point A and point B. And then I'm going to need an expression for the normal vector. And the normal vector has two parts of it. One of it, which is to calculate the size of this area, which would be, let's call this dA. Of course, we're dealing only with 2D here, so our area is really the length of a line, which is given by dx squared plus dy squared, and then the vector has components, which would be dy ex and minus dx ey. And the signs are important here because it's clear that as we've drawn here that that dx and dy are positive steps, but you can are positive steps dx and a positive step dy. But it's very clear that the normal vector is pointing in this direction, and so that gives rise to this minus sign right here. The way I always convince myself that I've done this right is by taking limits. I'll convince myself that it's right in various limiting cases. And so, for example, I might think about a couple of simple cases. Let's think about the case where maybe dy was equal to 0. Then we might have flow through a material like this, where n is like this. Here's point A, and here's point B. And if I put that in, then it's very clear that if I put dy into 0, then I get nothing out of this component. And now n is equal to this, and I get dy is equal to 0, so dx and this cancels, and then I get that n is indeed equal to minus ey. Similarly, I might take a point A and I might think about an orientation where it goes to this, and now my normal vector points like this. And again, in this case, we'll find that n is just equal to ex, because in this case, dx is equal to 0, and my length of my line is just dy. So hopefully that convinces us that we've done this right, and we've now got all of the information that we need to put together to understand why the stream function is so useful.